Yes, so Stephen is opening the technical program. He's been a master student at Utrecht, and now he just recently started his PhD at Kent, and he's going to talk already about work that he's been doing there.
Yeah.
So, thank you.
Thanks for the introduction and welcome everybody. So, I'll be talking about our ongoing work towards modular reasoning with monadic effects. So, and I'll outline our approach to that. So let's just dive in and talk about modularity. So, modular approaches are used throughout software engineering in order to build software. So in a simplistic view, we've got the following. We've got components, Cs, which are then combined to build software system S's. So this has several benefits. First of all, components may be reused. So reuse of code means we don't have to, recode it. So we speed up development, reduce costs, but it also improves software quality. Another benefit is that it's easier to maintain systems in that way. So a key concept also going on here is abstraction. So the components define an interface that is available then to build the software systems, but they hide the specific implementation. So in terms of maintainability, we can then swap a component for another one which has the same interface, and the system should still work. So this is very well established. But what we would also like to do is establish properties about our systems in order to ensure correctness of them. What is usually happening, or what is often being done, is that we prove those properties in terms of the whole composition, and this breaks the whole modular approach to this. So, first of all, if we do proofs in this style, then part of the proofs are basically redone for each of the components that is reused, which is bad. Another thing, if we swap a component for another one, we might have to redo the whole proof. So what we would like to do is to have the same benefits for reasoning about programs as we have for building them. So we would like to do it in a modular way, so we would like to prove first properties about our components. So these properties can rely on specific implementation of the components, but then hide the implementation again. And, well, we establish the properties of the systems in terms of these properties, and independent of the specific implementation of the components. Okay, so let me also outline the context in which I want to do this. So I'll be talking today about doing this in the context of polymorphic monadic mixing components, which is work by Oliveira and others. So let's look at an example. So this is a component for calculating the Fibonacci numbers. So there are two important aspects to this. First of all, note that it is defined using open recursion. So instead of performing the recursive call directly, we call an oracle that has been given to us. Another thing is it's written in monadic style. So we have a monad M, but we don't really use any specific monad implementation operations other than return and bind. So it can be any monad, and we're polymorphic in it. So essentially, Fib doesn't produce any side effects except for those that arise from the calls to the oracle. So we say that it's a pure component. So how can we define a Fibonacci function? Well, we can first close the open recursion, then pass ourselves in, so this is done by new, and then run it in the identity monad, so we get a function which computes the Fibonacci numbers. Okay, but, well, this function is kind of slow, so it has exponential running time. What we can do is perform memoization, and, well, we can do it in a modular way. So we can define another component which does that for us. So here's one, memo. It's again written using open recursion. And, well, it performs a stateful computation. So we've got a lookup table here in the state, which is just a list of pairs. What we can then do is perform state operations, so get and modify to consult the table and then update the table. So again, notice we don't use a specific monad here, so we don't use state, but we have a constraint, a state monad constraint on the type variable, and we quantify order. So what we can easily do is then compose fib and memo. So the constraints are then combined, so it has to be a monad, okay, and it has to be a state monad. And well, we can then close the composition, and we get a function that is that defines a stateful computation, so we can run it in with an initial empty table in order to get a faster Fibonacci function. So we've got the following situation. We've got two components, fib and memo, which we use to define two functions, slow fib and fast fib. So what would be an interesting property to prove about those? Well, that they're actually the same. So what we want to prove is that adding memoization to fib doesn't change the behavior. It's non-interfering. So if you now think in terms of reuse, well, we could perform memoization on other functions, and well, we can even perform it on a whole class of functions so that it's non-interfering. We didn't really have any constraints on fib other than that it is pure, and memoization should work for any other pure component. So we can replace fib here by f, and it should still hold. Well, we might want to do even more. So let's assume we've got a third component, log, which well, you can think of as logging the number of recursive calls or something like that. So it has a brighter monad constraint, and it accumulates in the monoid. So if you compose this with the previous two, well, we can then run the brighter monad and the state monad. So this is the monad that we're instantiating it with is a brighter state monad, and we get another function. But wait, what if we discard the log we've just recorded? Then again, we should have a function that is equal to the slope function. So how would we go on and reason about this? Well, several things have been proposed and used to reason about monadic computations. Someone advises that we can just unfold monad definitions. But if we think about establishing properties about components, we don't have a specific monad available yet. So the monad is fixed once we define the whole composition. But for components, we only have a constraint on them. So we can't really unfold monad definitions because it's not available. Another thing, well, if we've got monad polymorphism with parametricity results for it, then we can derive three theorems. So specifically, Keuchel has a paper about deriving three theorems for type constructor classes such as monad. However, unfortunately, those three theorems are not strong enough to prove the non-interference we are interested in. So what we can also do is use algebraic laws about monads. So for example, for state, when we perform a put and a get and then a put of that exact same state, well, it's actually no all. So this kind of works, but it's limited. because we still have this oracle going on, and when we reason about a component, we don't know what the oracle is, and we don't even know which side effects the oracle is using. So this also causes problems. If you think back, well, how do we actually describe our mixins? We've got a functional representation that uses open recursion and monad polymorphism. And these are two bad properties. So what we would like to do is actually replace them by, well, the good properties. So it should be first order and monomorphically typed. So what would be such a representation? Well, fortunately, people have looked at it before in the context of reasoning. So there exist strategy trees which do just what we want. So there's earlier work by Hoffman and others, and also the third talk, and they will be again about strategy trees. On top of that, they are defined by induction. So we've got an induction principle available which we can use for reasoning. Okay, so let's look at strategy trees. And here's the definition. But it's good being explained with an example. So here's a strategy tree implementation for the Fibonacci component. So the tree has two constructors. It has answer and query, which well, encode a finished computation. So we return an answer, which is the first constructor. So you can see that in the base cases, we just can immediately return because we don't perform any recursive calls, and then we also produce an answer in the step case. So what is query? Query encodes, well, that we should perform a call to the oracle. So in essence, we don't perform the call ourselves, but we externalize the call. So we have got the parameter I available that we call the oracle with, and then we get an answer from the oracle O, which we use to continue the computation. So we've got a continuation function which gives us another strategy tree then. So, well, and if you look at FibT, this is exactly what we wanted. It's first order and it has the monomorphic type, so we're quite happy about that. But wait, it does not really work for Memo, which is bad. As we've seen, Memo uses get and modify, so these are state operations. And there's no way to encode them yet. So tree can unfortunately only represent pure mixins, whereas Memo is not a pure mixin. So we have to come up with something new. So we generalize the strategy trees and look at strategy trees for monadic effects. So here's another definition for stateful computations. So if you think back what answer and query meant, so answer is that's the final result, but when we have got a stateful computation, we also have got a final state that we write in. So we have another field that stores it. And well, whenever we perform a call to an oracle, we arrive at an intermediate state just before the call, which is stored here. And then the continuation function, so after we return from the call to the oracle, gets an updated state. And then we can produce another strategy tree which continues. So we can then use this to define a strategy tree for Memo. So here it is. So for form to look up, if we're there, we can just return. Yes.
Oh, yeah, so I have a question. So what you're doing here is you're extending your previous strategy to new state parameters in the constructors, right?
Yes.
Would it be better perhaps to, because that seems like quite an ad hoc extension, because
Yeah.
maybe there's another, but maybe we can address this later on.
Yeah. So wait 2 slides.
Okay, then I'll see
Yeah, so this is very important. Where were I? So answer produces the final, well, if it's in a table, we can just return it, and the table is unchanged, and else we perform a query, we get the value in an updated table, which we then modify with the new element. Okay, so this is fine, this is nice, so we can represent hammer, but it's also very ad hoc. And, well, other ad hoc definitions are possible, so we can give definitions for exceptions, for failure, for non-determinism with lists, for read and write among us. But, well, there's still much more going on in the background, so I haven't shown you, but actually you have to perform conversions from the functional representation to the strategy tree representation. And moreover, you have to prove that those are actually equivalent. And, well, if you give ad hoc definitions for all of those, you will have to redo the proof all over again. And, well, we don't want to do that. So we would like to know what the underlying structure is and exploit the underlying structure in order to perform a generic derivation of those representations. So whenever we search for some underlying structure in data types, what we usually find is a monad. So there it is. Tree is actually a monad, and here you've got some elements. It goes by several names. It goes by coroutine monad, which we usually call it, but it's also been called suspension monad, assumption monad, or step monad. So the important thing to notice is here that suspension is a monadic effect, and this also gives us a way to get strategy tree representations for other components which have different monadic constraints. So whenever we have got state like from Hemo and well, we've got suspension going on, how do we combine them? Well, the textbook approach is to use monad transformers. So here it is, here's a coroutine transformer to do that. So let's look at it a bit more closely. So what do we do? We start our computation in the inner monad, so we perform a stateful computation until, well, we get to a point where we are either finished or we perform an oracle recall and we suspend at that. Yeah, and C is then basically the library you've seen before. So the nice thing is with this transformer we can explain, well, a range of strategy trees for a range of effects. So when we combine coroutine with the identity, and you can see that it was just a tree definition we had earlier. But if we combine it with the specific state monad, state S, we get something that is isomorphic to the ad hoc definition I've just shown you. So we get strategy trees which work for the monadic constraints on the right. Unfortunately, this does not work for all constraints. So exception and the reader monad constraint, the strategy tree representation we get is unfortunately not the one we would like to have. So the semantic doesn't really follow this up. And however, you can define ad hoc definitions for those and use them. Okay. What you will find in the paper. So you will actually see the conversions between the functional representation and the strategy representations for state monad and the list monad. Well, exceptions did not work, but we can give an ad hoc definition. You will also find that in the paper. And moreover, you will find a characterization of effects for which this works and for which it doesn't. Okay, so what have we seen? I've given you a characterization of monadic mix-ins in terms of strategy trees. We first looked at at strategy trees for pure components, and then we generalized this to strategy trees for Keuchel components, and we've also looked at a systematic way to derive those, at least for a range of effects in the coroutine monad transformer. So, if we recap, where are we actually going with this? So, our application is modular reasoning. So, we have applied this to perform some proofs, which is nice, and well, we would like to do some more. But there's also much more work on the representation. So, the coroutine transformer as it is now, well, it doesn't have our effects, we would like to generalize it. In order to do that, so we need some to exploit some category theory in order to get there. So we've got some ideas about using associated adjunctions of a monad in order to get the structure that we need. But there's also still work in the correctness. So in the paper of Bauer, so the third talk today will prove that actually the strategy tree representation and functional representation for Q components is the same, but there's still work to be done to extend that proof to other effects. So we've got the proofs for specific components, so like the memo component, we know that it is the same, but we don't know it for all components. Yeah. Thanks.
Thank you. So does anyone have any questions for Stephen?
So when you showed us this example of extending the tree to the state moment, you can put up the slide. Right. So, so I was just thinking, so here, this is just the same structure as tree, except that the parameters are then tuples, I times S, O times S, A times S. Which means that basically you've changed just the underlying category of tree. So tree is initially a functor that acts on C times C times C, where C is, let's say, the Haskell kind of category, and now you have changed the category, and it's S times C, S times C, S times C. You see what I mean?
I don't, unfortunately.
So here, it's the type of answer is isomorphic to having a pair, AS, into tree, and it's the same pattern everywhere, right? Yeah. So instead of A, we have the pair AS. Instead of I, we have the pair IS, and instead of O, the pair OS. Yeah. So if we were working with a category where all our objects were of type something S, then that would just be exactly the same as tree before. So you haven't extended in a certain sense tree, but specialized it. Yeah. You've changed the category to a more special one. Would this view of things work? I mean, you obviously haven't looked at that. So I think whether this isn't more general than the monad transformer. Yeah.
So yes, it works in this case. However, I don't think it works in all the cases. Just to specialize the category, because.
So you have to look at the reader monad.
Yeah, you would have to look at the reader monad, and there you can see it, and also for exception.
So you say that the reader monad doesn't. Yeah, but the reader monad is very simple because it's just the explanation.
Yeah.
Oh. Thanks.
Yes.
So what you're basically doing here is you're making recursive calls explicit. Right? That's what the query constructor does. And then you run into the problem that if you have other effects, you have to combine them using monad transformers, and then this gets complicated to combine with tree structure. So the question I have, wouldn't it make sense to make the other effects that you're using also explicit in the tree data type? For example, you could add constructors for, let's say, read and write to the tree data type if you're interested in state. And in that way, the structure you have is very similar to like a free monad, which is very easy to manipulate and to add new constructors.
So the problem with that is that that free monad isn't really a state monad. So it doesn't fulfill the algebraic laws we have we need for state monads.
No, but you can, okay, so the free monad is just the syntax, right?
Yes.
And that's something you can expect.
Okay.
And then once you've built up this thing, you can define an interpretation which actually runs it, which translates real state monad and goes in recursion with real recursion, that kind of thing. And that's kind of, I think, in spirit, similar to what all the work on handlers and which is going on recently. So I think that's really interesting.
Yeah, so this would give you, well, basically a convenient syntax for doing this. However, the representation isn't the same, so you can't prove that this representation is equivalent to the functional representation. You can't go back and forth between them.
Is that, but it's like saying...
Yeah, the question is that a problem?
Because it's like saying, if I have my syntax in one hand and then I run my semantics, then these are different things. Yes, that's true. But, okay.
One last question then?
Oh. Two last questions.
No, do you want Ralph was first?
I was expecting to see some proofs at the end.
Oh. Well, I said in the beginning this is towards reasoning. It wasn't specifically about...
And I had a microsleep at the beginning. Okay, can you give us sort of an indication what they look like? So the rough feeling what I have to do if I were to use your framework?
Perform induction over the trees. That's what you do.
Do they look attractive, the proofs?
Not yet. Oh, I'd say. Well, they are too long.
Okay, I suggest we take further discussion offline. Let's thank Stephen again.